Good afternoon. The title of our project is an investigation in secret sharing. Our team number is 51079. We are interested in the threshold scheme. When a sequence is divided into empty shadows, any t shadows or more can open the secret. Otherwise, any t-1 shadows or less cannot open the secret. We found a problem. When 11 persons keep a sequence and any 6 of them are allowed to open it, we need 462 locks and each person needs 252 keys. We call this problem KD611. We found the solution of KD scheme. Let's see the solution of KD-V5. First, we cannot not have a column of 3 zeros because of the conditions of availability. In these examples, P1, P2, and P3 cannot open L1. Second, by the conditions of confidentiality, we need to block all 2-person groups. A column of 1 0 cannot block any 2-person groups. It is useless. Therefore, each column should have exactly 2 zeros. By the conditions of confidentiality, we need to block all 2-person groups. Finally, we have the solution of KD-V5 in page 7 of our project. The fundamental solution of KD-TN is that each lock has a column of t-1 zeros. The locks consist of all different t-1 number combinations of zeros. The following are the properties of the fundamental solution.
Chinese remainder theorem scheme. We take the consequence of a secret number x as follows. yi equals x modulus mi, with mi are pairwise relatively prime, and they are in ascending order. The yi are the shadows with the conditions of availability and confidentiality. In order to satisfy the condition of availability and confidentiality, we have the following inequalities. We have 3 methods to have a more secure CRT scheme. First, large number of possible value of x. Second, mi are larger. Last, mi are closer to one another. We create a secret sharing model and make some assumptions. The assumption is to ensure that insufficient number of shadows cannot obtain any part of the original information. Our report only focused on the threshold scheme. Alpha measures the maximum possessions of a shadow, and beta measures the minimum missing for t-1 shadows. When the case t equals 1, this is meaningless to discuss. We compared KD and CRT scheme. Alpha and beta of KD differ from the ideal values significantly for non-trivial cases. When gamma 1 is close to 1, alpha and beta of CRT are very close to the ideal values. In the remaining of this report, we need to find large and close PRP numbers. By the prime number theorem, we cannot simply take mi as primes. Therefore, we create an algorithm to generate enough PRP numbers. 3 consecutive integers starting from an odd gives 3 PRP numbers. where n is not divisible by 2 and 3, n plus 2, n plus 3, n plus 4, and n plus 6 gives 5 PRP numbers. We try to extend the set of PRP numbers to a larger one. We use the following table to extend the set. We observed the result and got 2 methods to generate TRP numbers. Details are in Appendix C and D at page 28 to 31 of our report.
Before discussing the first method, we define Pf of x equal to the set of prime factors of x. Two numbers are relatively prime if and only if their prime factor sets are disjoint. The first method is m plus 1, m minus 1, and m plus pi. If pi are the smallest of prime, we propose that for all p, which is a prime between 2 and p n minus 2 plus 1 over 2, such that p divides m. Then m plus 1, m minus 1, and m plus pi give a set of PRP numbers. Then we are going to prove that m plus 1 and m plus pi are relatively prime. First, m plus 1 and m are relatively prime. Their prime factor sets are disjoint. Second, the prime factor set of pi minus 1 is a subset of prime factor set of m. With reference to the figures, the prime factor set of m plus 1 and the prime factor set of pi minus 1 is disjoint. Therefore, m plus 1 and m plus pi are relatively prime. Similarly, m minus 1 and m plus pi are relatively prime too. Then we are trying to prove that m plus pi and m plus pj are relatively prime. First, the prime factor set of m and the prime factor set of m plus pi are disjoint or intersect at pi. Second, the prime factor set of pj minus pi is a subset of prime factor sets of m. Third, pi does not belong to the prime factor set of pj minus pi. With reference to the figures, the prime factor set of m plus pi and the prime factor set of pj minus pi are disjoint. Therefore, m plus pi and m plus pj are relatively prime. M plus 1 and m minus 1 are relatively prime. Since they are consecutive odd, we propose that therefore m plus 1, m minus 1, and m plus pi is a set of PRP numbers with the following conditions.
Before discussing the second method, we define omega xk is equal prime factor set of x with prime factors counting from 1 to k. A and B are relatively prime if and only if the omega ak and omega bk are disjoint, where k is not less than b minus a. First, we tabulate the value of m modulus p, where m counts s to s plus k, and p are the primes counting from 1 to k. Second, we pick up the value of mi with omega mik are disjoint sets. In this report, we found XPRP's number from 51079 to 51100. We use this table to get the previous result. After doing some tests on shift for PRP's numbers, we guessed that number of PRPs found within S to S plus k is approximately to pi k. This is the end of our presentation. Thank you.